So, please, Carroll.
Thank you very much. The microphone at the right level for those. It sounds very loud. Yeah, it's good. Okay. Also, this is an embarrassing thing to ask. Is this the right talk? Is this the thing that was advertised that I was going to give? Yes? Okay, because I had lots of different talks I could give, but I should give the one that you thought you were going to come to. It's great to be here at Cal Poly, and I need to always start this particular talk with an apology rather than saying something bragging or anything like that. The point is that the title sounds a little grandiose, and I know that. And there's a long history in the history of science, the history of physics, of physicists, professional, highly trained physicists, looking around at other intellectual disciplines, whether it's philosophy or climate science or psychology, and saying to themselves, how hard can that be really? I'm a physicist, I'm smart, I can just waltz in there and figure everything out. So I want to promise you that is not what I am trying to do in this particular talk, even though the subtitle refers to the origin of life, meaning in the universe itself. I'm not actually going to tell you what happened at the origin of the universe, at the origin of life, or the origin of meaning. I'm going to try to make the case that we can talk about these things in a sensible, coherent, natural framework, but these are questions to which the answers are not completely there. There's a lot of work left to be done. So consider this talk more of an encouragement to carry on a conversation that is me telling you what the final answers are. And I'd like to start, as a physicist, with a little physics thought experiment. So imagine you were driving in your car, and you run out of gas. What happens? This might have happened to you. This did happen to me once in my life. I was in a rental car. It's not my fault, but the answer is your car stops moving when you run out of gas, okay? Unless you get out and you push it. This is a very natural feature of things in the universe. If you have an object, here's an object, and you put it on a table, and you say, what happens to it? It doesn't move all by itself. You can start it moving by pushing it, and then when you stop pushing it, it stops. Okay? A natural, true feature of the universe. So if you were 2,500 years ago, and you were Aristotle, and you were trying to figure out how the world works, you would take this feature of motion as a fundamental feature of reality. You would say to yourself, there is something inherent, intrinsic in the nature of objects. They have a natural state of being, which is typically at rest. And to change them in a state to go from rest to moving, you have to exert something. You have to exert a force, we would say in modern parlance. And then when you stop exerting the force, they stop moving. Okay? He's not wrong. Modern physicists love to make fun of Aristotle for being wrong about many, many things. But we just did the experiment, and it was true. When I stopped pushing, it stopped moving. So you go from this supposition to an entire way of looking at the world. Okay? That to not only to every motion there is a force or a mover, but to every effect there is a cause. And Aristotle develops an elaborate metaphysics of causes and effects. There's many different kinds of causes, there's many different effects they have, and so forth. And for many, many years, this is the way we thought the universe worked. You will not be surprised to hear that I'm going to tell you that it's not how the universe works, but it's a little more subtle than that. So over the years, this idea was pushed forward by philosophers, because there weren't any such thing as separate category scientists at the time. So this is Aristotle on the left, this is Spinoza, and this is Leibniz, and they developed Aristotle's ideas into what we now call the principle of sufficient reason, which is basically the bumper sticker that you can buy in any knick-knack store that says everything happens for a reason. Or in more technical terms, to every effect, there is a cause. There's a reason why things are happening. It's closely related to the idea of teleology, that there's a goal toward which things move, whether it's the universe or some part of it. And you might have forgiven the philosophers for wondering whether or not the goal of the universe was ever more grandiose hairstyles for philosophers, since that's clearly developed over the years. Leibniz had artificial help, but the big news is that all of this is wrong. It's not true that everything happens for a reason. It is not true that the best way of thinking about the world at a fundamental level is a story of effects following causes. There's a big discovery of physics. I don't even need to say modern physics. It goes way back. And interestingly, we never tell you this. Okay, you can buy physics books, popular physics books. You can learn about relativity and quantum mechanics, string theory and the multiverse, and we don't tell you some of the basic truths, okay? For example, that cause and effect are not there at the fundamental level of the universe. It's not that anything goes, but that the right way of thinking about what happens one thing after another is a different vocabulary than the Aristotelian notions of cause and effect. Some people have tried. This is Bertrand Russell in the early 20th century. He was a philosopher again, so he cared about these things. And he said, the law of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone age. Surviving, like the monarchy, he couldn't help himself, even when talking about causality. He was British, he was not very fond of the monarchy, only because it is erroneously supposed to do no harm. So the idea that Russell is trying to get across is we have a better way of thinking about the fundamental reality of nature than Aristotle's causes and effects. But we don't tell you, we don't bother, because we figure, what's the harm in not telling anybody? So I'm here to tell you, and I think it's kind of important. Why it's important is because it's a big step in reconciling two different ways of thinking about the world. What the philosopher Wilfrid Sellars labeled the scientific image of the world and the manifest image of the world. The manifest image of the world is the world we immediately see, the world we're used to on an everyday basis, a world that is populated by things like tables and chairs and cows and horses apparently on campus, and causes and effects and reasons why. This is the world in which what Aristotle said about motion is just completely true, okay? But as science progresses, we learn more and more about the world, and it's not just that we gather more facts. We do that, but we put those facts to use, and not only do we gather more facts, we gather facts that are in regimes that are far away from our everyday lives. So in one sense, it should be very unsurprising that what we learn is a very different kind of thing than what we would think about just by looking at everyday reality. And we develop, therefore, new theories of the world, which constitute the scientific image, that speak very different languages. It's not just an improvement quantitatively on what Aristotle said, but a whole different kind of toolkit for thinking about how reality works. So in the manifest image, you know, like that time flows from past to the future. For every effect, there is a reason, and so forth. The scientific image says that time does not flow. That's the best view we have in modern physics. Rather, time is just a label. There's nothing special about the moment now. Every moment of time in the history of the universe is equally real, according to our best current understanding. Rather than causes and effects explaining the motion of particles and features of the universe, we tell a different kind of story based on patterns and, as you know if you're physics students, differential equations in particular. So there's a long list of differences, and my purpose here today is to tell you how we can go about trying to reconcile the manifest image with the scientific image. Because the manifest image isn't wrong. There are cows and planets and people in the universe, as well as atoms and molecules and forces. These are both real things. It is true that in our real world, to get something moving, you have to push it. At the fundamental level, that's not true. How do you get from there to here? That's what we're going to be about. So as I mentioned, we can move in, using science, to regimes of reality very different than our everyday experience. So one of the steps along the way was taken by this guy, Ibn Sina. His name is sometimes Latinized to Avicenna. He was a Persian polymath in the year around 1000, during the height of the Islamic Golden Age. And to someone like me, a modern theoretical physicist, Ibn Sina is extremely annoying. And that's because he was a doctor. That was his day job. Like, you know, during the day, he thought about the health and anatomy in people's bodies and making them better, and he wrote many books about that stuff. And on weekends and in his spare time, he would propose new fundamental laws of physics. This is very frustrating to someone whose job it is to do that today. It's much harder. The low-hanging fruit has kind of been picked. But one of the things put forward by Ibn Sina is in response to Aristotle, who said that in order for something to move, you need to keep pushing it. Ibn Sina was sort of the first to pinpoint the idea that the reason why things stop moving when you let them go is because they're not in vacuum. They're not in empty space. There's something tugging on it. There's a frictional force, a dissipative force. And he said if we could imagine a true vacuum, empty space, then something that was moving with a certain velocity would just keep moving with that velocity forever. This is a profound idea, that something would move without anything pushing it. Of course, today, it's second nature to us. We build things that are out there in the vacuum, and they do, in fact, just keep moving. This is the Voyager 1 spacecraft. It's moving away from us. It's not going to come back because its rocket engines are all dead. There's nothing pushing it. Therefore, it's going to keep moving. We make this sort of dull and dry and pedantic by labeling it the conservation of momentum. And then we torture you in your physics classes with inclined planes and frictionless surfaces and so forth. But you should stop to reflect on how fundamental a difference this is. This is not just things behaving differently. This is what the world is made of is very different. It's not just there are things and they move a little bit differently than we thought. But in Aristotle's world, the notion of a force, a pusher, a cause of motion was absolutely central. In Ibn Sina's world, things just move. You don't need a mover, okay? Aristotle used his argument to prove the existence of God, because there's lots of things moving in the universe, therefore something must be moving them overall. There's an unmoved mover, which is God. That particular argument goes away if you believe that things just move by themselves. Ibn Sina did not say that, of course, but it is one of the consequences of this way of thinking. And it goes much further than that. We skip a few hundred years of intellectual history to go to this guy, Pierre-Simon Laplace. Now, Laplace is living in a very different world than Ibn Sina was. Ibn Sina was living in a world where intellectually Aristotle was the boss man. By the time 1800 had come along and Laplace was there, Isaac Newton was the boss. He had given us classical mechanics, and we thought we knew how physics worked at a fundamental level, what we call the clockwork universe. But even though Newton had written down the rules of classical mechanics, it was really in some sense Laplace who appreciated their implications deep in his bones for the very first time. Laplace says it's not just momentum or energy that are conserved, it's information that is conserved. If you think about that typical physics problem where you have a frictionless surface and you scatter billiard balls, right? So how would that be set up if you were given a problem set? You'd be told what the billiard balls are doing at the start, and then you would use your differential equations and you would see how they move together. Momentum is conserved. They would scatter off each other at a certain angle. Okay? Laplace points out something that is implicit in Newton's description of this system. Namely that you could be given the velocities and positions of the billiard balls at the end of the experiment. You don't have to be given them at the beginning. You could wind the clock backwards and you could get exactly the same answer for the whole trajectory of the universe. In other words, the whole history of this system is determined, it's implicit in the state of the system at one moment in time, any one moment in time. They're all created equal. He invented what we later dubbed Laplace's demon, but what he called it was just a vast intellect. He says, imagine a vast intellect which knows everything about the world. So as a Newtonian thinker, what he meant by that was the position and the velocity of everything in the world. This vast intellect has infinite calculational power and knows all the laws of physics. And he says, to that vast intellect, the past and future are as transparent and known as the present moment is. Because you would just instantly know everything that could happen all throughout history. So this is called Laplacian determinism. It bugs some people. You worry about your ability to make choices and free will and things like that. We'll get to that in a bit. But first, the thing to point out is that it's not just that the universe moves and keeps moving. It's that there isn't any such thing as the question, why is it moving? That's not the kind of question that Newtonian mechanics lets you answer. Why do the billiard balls end up in this position? Well, because they started in that other position. But Laplace says you could just as well say, why did they start in that position? Well, because they were going to end up in that other position. Okay? It works equally well, forward and backward. So instead of causes followed by effects, the story of the universe is a story of patterns. Think about the real numbers, right? -3, -2, -1, 0, 1, 2, 3, etc. There's a clear pattern. There's not like chaos breaking out, right? If I give you a number, you can tell me the number before and the number after. But no one says the number 4 is caused by the number 3. It doesn't make sense. It's just the next number in the pattern, okay? It's not that one number is leading to the other, it's that the whole set of them all together obey a certain rule given by number theory. Laplace says the universe is like that. It's not causes and effects, it's just a pattern obeyed over and over again, the laws of physics. Of course, today we know that what Laplace thought the laws of physics were is not correct. We have a better idea. And one of the dramatic claims I want to make for the talk is this one. The laws of physics underlying our everyday lives are completely known. This always gets me into trouble when I make this claim. People don't want to understand exactly what I'm saying, so let me be very, very clear about what I'm saying here. I'm saying the following thing. You and I have atoms in our bodies. I hope I'm not being controversial yet, okay? Whatever else might be going on, there are atoms inside us. And these atoms have electrons, protons, and neutrons, right? There's a nucleus in the middle, made of protons and neutrons, electrons orbiting around. We know from particle physics that those protons and neutrons are really made of quarks. They're held together by something called a strong nuclear force. The electron is held to the nucleus by something called the electromagnetic force. There is a force that pulls everything together called gravity. There's a sneaky fourth force called the weak nuclear force, which you wouldn't really notice in your everyday life if it weren't for the fact that the sun is shining. The sun shining really depends sensitively on the weak nuclear force because it can convert protons and neutrons back into each other and therefore allow nuclear fusion to happen, okay? And then when that happens, when you convert a proton to a neutron or back, you emit a fourth kind of particle called the neutrino. And all of these particles are swimming in the background called the Higgs field, right here. There's a field, invisible energy field pervading all of space called the Higgs field that affects the particles that move through it by giving them mass. So the mass of the quarks or the electron come from that Higgs field. And we only discovered it in 2012. I wrote another book about that. You can buy that right now on your iPhone. You don't need to wait. You can do it on Amazon right now. So we now know, so the statement that you're willing to agree with already is that there are these particles in your body. The statement that you might not think about, but I'm going to claim is true, is that those are all the particles that are in your body. And we know how they behave. We know the equivalent of Newton's laws for those particles. It's a set of rules under the rubric of quantum field theory. It's a little bit more subtle than Newton's laws, but we know what those rules are. So I would take hours to give you a really persuasive case for this argument, but I want to at least give you a little bit of hint of the reason why we think this is true. It's not just that, well, we found these particles and we haven't found any others, therefore we're probably done. It's completely the opposite of that. We're sure there are other particles. There are top quarks and bottom quarks and so forth, tau leptons rather. There's probably many more particles that we haven't discovered at all. There's probably dark matter particles, supersymmetric particles might be out there, who knows. None of those are in your body. None of those particles, none of those forces or fields play any role whatsoever in making you who you are. We can have plenty of new discoveries in physics. I'm not making the traditional mistake of claiming that we're almost done finding all the laws of physics. I'm making a very specific claim that we know the laws of physics that make up you and me and everything you've ever seen with your eyes, touched with your fingers, tasted with your tongues, etc. That's already a pretty dramatic claim, even though it's not as dramatic as it could be. So let me see if I can convince you. The first point is, of course, many people will say, well, I'm not going to believe any claim you make about the laws of physics if all you do is show me a cartoon. I am a hard-boiled natural scientist. I would like to see the equations behind this claim. So here you go. This is the claim. This is the equation of what we call the core theory. This is the name invented by Nobel laureate Frank Wilczek. It combines two theories together. One of them is the standard model of particle physics. The other is general relativity, Einstein's theory of gravity. Okay? Now, I'm not going to go through all the details. Sorry. But, by the book. But this is the equation that would be used by the modern day version of Laplace's demon, trying to understand the physics that makes up you and me and what's going on in this room right now, okay? So you see all the different ingredients there. There's quantum mechanics, space-time, gravity. These are the nuclear forces and electromagnetism, the particles that make up you and me, the electrons and the quarks, and then finally the Higgs boson. This is the equation that will tell you if you give me the initial conditions for what these particles are doing, I'm going to tell you where they go. Or vice versa, they can go backwards just as well. So what you don't see in this equation are causes and effects. What you don't see are reasons why. This is the equation. This is what the experiments tell us the equation is, okay? You want to say, well, why is the mass of the Higgs boson such and such a number? Maybe there's an answer to that, because maybe this theory is not complete and it's part of some bigger theory, etc. But at some point, we're going to have the complete theory, and then the answer will be because that's the way it is. It's not that there is something that causes this to be this way. This is how the universe works, and that's our best current understanding of reality. Many of you will say, I like equations, I'm glad you're showing me the equations, but I only trust equations that will fit on a t-shirt. So I can do that experiment too. We can demonstrate empirically. You can buy this on my website. I don't make any money off of this. I'm not very good at it, but you can get the core theory t-shirt if you want. Okay. So if you're like most people, you're probably willing to go with me when I say like there are electrons and quarks inside your body. You might be more skeptical when I say there's not going to be any other new particles. Okay. So there aren't any new particles that affect your body or this table or anything like that. So it's not that we're done with physics, it's that we know some things. We don't know everything, we know some things. And people get a little nervous about that. They say, well, you know, science never really knows everything perfectly. We should always be willing to learn new things, which is true. But even as we learn new things, there are some things we don't let go of. When I say that this table is made of atoms, okay? 300 years ago, we didn't know that. No one would have said this table is made of atoms. Now we know it. That knowledge is never going away. There's no future physics discovery that says, oh, yeah, the whole atom idea, that was wrong, that was sort of off base. Okay, the atoms will always be there. We might understand better what they are, we hope to do that, but they will always be there. So how do we know that we're not missing anything in this equation? There's not some important influences that are not being taken into account. Well, I'm glad you asked. I'm glad I asked for you, because there's a very powerful set of arguments based on the fact that the world we live in is governed by something called quantum field theory. Quantum field theory is the marriage of quantum mechanics and special relativity. It was put together by many people over the years. The basic idea is that when we talk about particles, whether they're electrons or quarks or photons or gravitons, that's not really what the universe is made of. What the universe is really made of is fields filling all of space. You've heard of the gravitational field, the electric field. I just told you about the Higgs field. When you start these fields vibrating and you look at them closely, you see them as individual particles. That's the magic of quantum mechanics, okay? So the light coming from these projectors are electromagnetic waves, but if you look closely enough, you would resolve them into individual photons. That story, waves, look closely enough, see particles, is true for everything in the universe. So the electron, which you think of as a particle, is really a vibration in the electron field filling the universe. And quantum field theory comes with consequences. One of the consequences is called crossing symmetry. And to illustrate this, I show you these little pictures called Feynman diagrams, invented by my Caltech predecessor, Richard Feynman. My claim to fame at Caltech is that I sit at the desk that Richard Feynman used to sit at. So there's like pilgrimages, people come visit my desk, you know, look at it. People ask, like, how did you get Feynman's old desk? And the answer is, Feynman's old desk goes to the Caltech theoretical physicist who is most senior, who is not senior enough to deserve a brand new desk when they get to Caltech. So that's me at the current. So what the diagrams are, on the one hand, they're ways of visualizing processes between elementary particles, but it's more than that. They're ways of calculating the probability of these kind of interactions actually happening. So imagine that you thought there were some new particles or forces that were relevant to how we live or think, for example. Imagine there was a consciousness boson that was important to elevating our thought processes above the merely inorganic, okay? Well, what would that mean? That means there was some new particle which interacted with some new interaction with the ordinary particles that are already in our brain. If you invent new particles or fields that don't interact with the particles that we know about, then they're irrelevant and they don't affect how we behave in any way. So we can rule that out right from the bat, off the bat. So if you want the particles which we already know are in us to be affected by some new particle, there has to be some new interaction. And you can say, well, this interaction, you read from left to right, so the particle comes in, it scatters by emitting some boson or something like that, and it affects the motion of the other particle. There's some probability that that happens. That better be a large enough probability that it's relevant. If it happens less than once per the age of the universe, it's not going to be really very relevant. Now, crossing symmetry says this following very simple thing. If you have a Feynman diagram that represents some process that happens, you can rotate it by 90 degrees, clockwise or counterclockwise. You will get another diagram. That's what we did here. We took these ordinary particles, we rotated clockwise, so now we get a diagram where the ordinary particles are coming in, annihilating into some new interaction particle, and then creating two of the new particles that we're talking about. You see how this diagram rotated 90 degrees gives you that diagram? Crossing symmetry is the statement that the size of these diagrams is the same. If the diagram on the left is big enough that there's a non-trivial probability of this interaction happening, then the diagram on the right is big enough that there's a non-trivial probability of this interaction happening. Which means that if there were a new particle that would be relevant to our biology or neuroscience, then we could make it by smashing together the particles we know about and looking for what was created when that happened. The good news is that smashing together particles is particle physicists' favorite leisure time activity. It's what we do, right? We build giant particle accelerators and we smash electrons together and protons together and neutrons and everything we get our hands on. And we see what comes out. That's how we discovered the Higgs boson, the top quark, and so forth. And we haven't seen anything else. Which means that, not that there aren't other new particles, but whatever new particles there are interact with the particles we know about almost not at all. Either they're so heavy that we can't make them, even very, very high energies, or they're so weakly interacting that we just don't make enough of them even to notice. So neutrinos, for example, we know about neutrinos. Neutrinos are zipping through this room right now, millions of them every second, and they're going right through your body. You don't even notice them. Particle physicists can notice them because they have precise enough instrumentation. They can find them, but it doesn't affect you and me in our everyday functioning. Any new particles that might be out there must interact with us much more weakly than neutrinos do. So there's no way they could possibly affect our functioning or going through our everyday lives. This kind of reasoning, there's more steps than that, but this is the kind of reasons why we think that the laws of physics underlying our everyday lives are completely known. Having said that, of course, those laws of physics, as I've already mentioned, are very, very different than what we observe in our everyday lives. So how do we fit them together? That is the project of emergence. How do we go from a microscopic level of description, a vocabulary of particles and forces in space-time, up to the manifest image of the world, a world of tables and chairs and peoples and planets and puppies and horses and stuff like that. These, I'm going to argue, it's not that the top level is an illusion. It's not that we're wrong to talk about tables and chairs. It's a perfectly real thing, a table, okay? It's very tangible and it's there. It's nowhere to be found in the core theory, but that's okay. It's what we call an emergent phenomenon. It's a different way of talking about the world, sort of stepping back a couple of levels and looking at a macroscopic collection of stuff. But that macroscopic collection of stuff has a reality all of its own. It is consistent with the underlying fact that it's made of particles and obeys the core theory, but you can talk about it without knowing that. You could talk about tables and build tables long before you knew what quarks and electrons were. So that's emergence. How do you get this different theory, which uses words like time and dissipation and reasons why, out of the more fundamental theory that speaks a very different vocabulary? Well, again, I can talk for hours and hours about how to do this. Let me give you some brief ideas along the way. And my favorite, as already mentioned, is the arrow of time. The fact that there is a difference between the past and the future. Okay, the least surprising thing in the world. We all know that there's a difference between the past and the future. We all used to be younger. We will be older. Sorry, spoiler alert. We're only going to get older as time goes on. Okay. It is easy to take an egg and break it. It is hard to take a broken egg and put it back together. You remember what happened yesterday. You might predict what happens tomorrow, but you don't remember what happens tomorrow. You can make choices about the future. You can make a choice right now. You say, this is the most boring lecture I've ever been to. You can get up and walk out, okay? I don't encourage it, but you could do it. But you cannot, right now, say to yourself, This will have been the most boring lecture I will ever have gone to, therefore I am not going to have gone. You can't choose not to have come to the lecture. You can't affect the past by your choices, but you can affect the future by them. Where does this come from? Where does this difference between past and future come from? It's not in the core, it's not in the fundamental laws of physics as we understand them. We invent something called the second law of thermodynamics, which is the statement that entropy increases as time passes. Entropy is the messiness, the disorderliness, the randomness and disorganization. Roughly speaking, and this is very rough, the universe goes from being orderly to being disorderly. So why does it do that, you're allowed to ask? Well, a famous physicist, Ludwig Boltzmann, explained why the entropy of the universe will be larger tomorrow than it is today. Why will the universe be a little bit more disorganized tomorrow? The answer is simply there are more ways to be disorganized than to be organized. It is very natural for entropy to increase. What he didn't explain is why the entropy of the universe was lower yesterday than it is today. So I'm here to tell you why the entropy of the universe was lower yesterday than it is today. The answer is because it was even lower the day before yesterday. You might ask why that's true, and the answer is because it was even lower the day before that. And this line of reasoning goes back 13.8 billion years to the Big Bang. The reason why the entropy of the universe has been increasing throughout its whole history is because it started so low that even 14 billion years later it hasn't had time to reach equilibrium in this maximum entropic state quite yet. So when we talk about the arrow of time, it's much like the arrow of space, okay? What do I mean by the arrow of space? Here in the room, if I let this go, I know which direction it's going to fall in. There's a difference between up and down here in the room, not surprising. But you also don't think this is an intrinsic feature of reality. You think there's an arrow of space because I live in the vicinity of some influential object, namely the Earth, pulling me down. Okay? If I were out in space, there'd be no difference between up and down, left and right. My claim is that the arrow of time is exactly the same way. We don't think of it the same way. We think of the arrow of time, the difference between past and future, is absolutely built into the nature of reality, but it's not like that. We perceive a difference between past and future because we live in the aftermath of an influential event, the Big Bang. And living in the aftermath of the Big Bang is just like living in the vicinity of the Earth. It gives an arrow to time, just like there's an arrow to space. Not intrinsic to the laws of physics, a feature of the environment in which we live. And I claim even more than that this feature of the environment explains all of the differences between past and future. It's not just that there are many different arrows of time. Sometimes people talk that way. Those people are being silly. There's one arrow of time, and it all comes from the fact that entropy is increasing over time. So let me give you one example. There's, of course, many examples. I just gave you many different ways in which the past is different from the future. Let's think about memory. We remember the past, but not the future. We have some kind of epistemic access to the past that we don't have in the future. Well, why is that? And what does that do with entropy? So think about my favorite example of a memory is a broken egg lying on the floor. Once you get physicists talking about entropy, it's all about either broken eggs or coffee and cream mixing into each other. The only two examples that we really know. So when I say a memory, I'm not talking about anything specific to neuroscience or your brain. I just mean any record of the past, a photograph, a fossil, a history book. So this egg, you're walking down the street, you see a broken egg on the sidewalk. I claim that is a record of a past event. Why do I claim that? Well, if you ask yourself, what is the future of the egg likely to hold? There's many different possibilities, right? It could just stay there, it could be cleaned up, dog could come by and eat it or something like that. But if you said, what is the past of the egg likely hold? With very, very high confidence, you bet there used to be an unbroken egg and somebody broke it, right? That egg did not spontaneously appear on the sidewalk in a broken form. There was a previous thing that you can confidently assume existed, an unbroken egg. Why is that? The answer is because deep in your mind, you know that the universe began in a low entropy state at the Big Bang. And so the difference between the past and future is not, if you just knew what we know right now, there's a broken egg. The number of things that could happen to the future of that egg is exactly as big as the number of things that could have happened in the past. The symmetry is only broken by the fact that the past had a low entropy, and therefore when we fill in from that low entropy past to the present, we go through the existence of unbroken eggs. Given the existence of a broken egg and nothing else, we would not infer the existence of unbroken eggs, it's only because we know that entropy used to be very low. We go, aha, I know how to get a broken egg. First make an unbroken one and then break it. That's why we are able to say that we know things about the past. Why is a photograph of you when you're 10 years old wearing a red sweater evidence that you were wearing a red sweater this day when you were 10 years old? Because given the low entropy of the Big Bang, that's the easiest way to make that photograph. Okay? This was the days before Photoshop. These stories were older. But the main point is that the fact that you used to be young and are going to get older, the fact that you can make choices about what to do tomorrow but not what to have done yesterday, all of these are conditioned on the fact that we know that the early universe had a very, very low entropy. That's another book that I wrote, by the way, but you can buy it right now. All right. So that's fine. People are usually able to go with me that far. Past and future ultimately goes to entropy. But there is one sticking point here. There's a couple sticking points here. Remember, our task is to reconcile the underlying laws of physics, the core theory, particles and fields bumping around, with the manifest image of the world, causes and effects, people and places and purposes. So what I taught you here is that the fact that we seem to be flowing through time can be reconciled with the core theory once you understand that the Big Bang had a low entropy. But there's a seeming consequence of this point of view, which is that the universe over time is just getting more and more messy, right? More and more disorganized over time. Yet, we clearly see that complex intricate structures like you and me have come into existence. How do you explain that if you're so smart? Why is it that if the whole history of the universe is a story of increasing randomness and disorder, that intricate orderly things like universities and lecture halls come into being? So the answer is that there's a difference between entropy and complexity. These things have a subtle relationship to each other. They're not exactly in one-to-one correspondence. So think about the other favorite example one has, coffee and cream mixing into each other. We can see these three pictures. It's obvious which is first, second, and third, because we all know what the arrow of time does. So on the left, you have a low entropy configuration. All the cream's on the top, all the coffee's on the bottom. On the far right, high entropy. Everything is mixed together. But if you think about it, on the left, the picture is very simple, right? All the cream's on the top, all the coffee's on the bottom. That's all I need to tell you. Completely describe the system. On the right, the system is again very simple. Everything's mixed together. It's in between, when there are complicated fractal tendrils of cream and coffee intertwirling with each other. That's when things become complex. Literally, if you took a picture of these three things and looked at the file size of your JPEG file, the leftmost picture and the rightmost picture would be small and the one in the middle would be bigger, because it requires more information to specify that picture. It turns out this is universal behavior, that if you start with very, 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 very low entropy and go to high entropy, you will start very simple, you will end very simple, and in between, you may or may not have complex structures come to be. It depends on the details, but you can have complexity. So the point is that entropy just goes up. Complexity first goes up and then goes down. The fact that there are complex structures in the universe today is not despite the fact that entropy is increasing. It's because entropy is increasing. Entropy started very, very high, there would be no complex structures in the universe. If entropy started low and stayed there, there'd be no complex structures in the universe. The existence of complexity is driven and preserved by the fact that entropy is increasing. And it's true not only for cups of coffee, it's true for the universe. Here's your very short introduction to the whole history of the universe. On the left, the beginning. This is actually not the beginning. We don't really understand the Big Bang itself. But we actually understand very well what the universe was doing a few seconds after the Big Bang. It was hot, dense, and perfectly smooth. So were there any cameras around? This is the picture they would take. This is not actual data. This is a white rectangle that I made in Photoshop, and then I tilted it. But that's what the universe would have looked like. It was the same everywhere, perfectly white. As time goes on, tiny, tiny ripples in the universe, tiny inhomogeneities grow because gravity pulls things together. Gravity turns up the contrast knob of the universe. So this is data. This is a picture of the universe at the cosmic microwave background, a few 100,000 years after the Big Bang. The tiny little ripples in color are differences in temperature from place to place because of this gravitational effect. This is the universe today, full of galaxies and stars. The galaxy that we see has about the universe we see has about 2 trillion galaxies in it. What's going to happen is that ultimately all these stars are going to fade away. In about 1 quadrillion years, 10 to 15 years from now, the last star will stop shining. It will have used up its fuel. Entropy will have gone up, okay? There'll be nothing left in the universe but rocks and black holes. And those rocks are going to fall into those black holes. That's 10 to 15 years. It's going to be a dull, cold, dark universe. But even the black holes don't last forever. In the 1970s, Stephen Hawking showed us that black holes radiate out into space. So if you wait for 10 to the 100 years, the last black hole will disappear and there will be nothing left but empty space. All the way along, entropy is going up, basically because space is increasing in size. But the point is, you start very simple, and you end very simple. And it's in between that complexity comes into being, just like the cream and the coffee. We live right now in the exciting, fun epoch in the history of the universe. You should count our lucky stars. Of course, that's necessary. We couldn't live there or there. So we're living when we can live. We're the interesting part of the history of the universe. We can pat ourselves on the back for that. Okay, so you say, fine. You're like acquiescing slowly to my sales pitch here. You're saying, fine, I can understand how the abstract notion of complexity can come to be, just in a universe governed by the laws of physics. But what about the specific kind of complexity that is life, right? True biological organisms. That seems harder to imagine that that's just going to happen through things bumping into each other according to the laws of physics. So I'll tell you a story. I was flying to a conference one time to give a talk, and I'm sitting on the plane, I'm reading some physics papers. They were about physics and the statistical mechanics of life, of biology, as one does on an airplane. And if you're a professional physicist, you get used to the phenomenon where someone hears that you're a physicist and they would like to tell you their theory of the universe. This happens quite a bit. So I'm sitting there reading papers. The guy next to me looks over at my paper and he goes, "Oh yeah, I've read those papers." I'm like, "Oh no, okay." And he says, "In fact, I can tell you the purpose of life." I'm like, "All right, well, it's going to be a long flight. I might as well be polite, right?" And he says, "The purpose of life is to hydrogenate carbon dioxide." Not the answer I was expecting him to give. It turns out I was sitting next to Dr. Michael Russell of the Jet Propulsion Laboratory, one of the world's leading experts in the origin of life. He actually did have a theory that was probably a pretty good theory when it comes to why life began. Now, we don't know how life began. Russell's theory is one of the many ones on the market. There are people who think he's nuts. He thinks everyone else is nuts. It's just everyone, it's a great field. Talk to anyone who works in the origin of life. They will say, yes, we're very close to figuring it all out, except all of my colleagues are completely nuts. It's hilarious. The point is that we have theories that are reasonable and might be right. So here is Russell's theory. He says that in certain regions of the early Earth, soon after it formed, there were regions where the entropy was much lower than it could be. In particular, there's a lot of carbon dioxide, CO2, lying around, in water, okay? So just as a matter of chemistry, if you take carbon dioxide, rip off the oxygen, replace it with hydrogen, so you turn the carbon dioxide into methane plus water, H2O, the entropy goes up, okay? In some sense, the carbon dioxide wants to be turned into methane. It wants to be hydrogenated. The problem is that the steps along the way are lower in entropy. So this is weird chemistry units. So high entropy is down here and low entropy is on the top. To go from CO2 down to methane, you have to first lower the entropy before you can raise it. So Russell says, here is a potential engine waiting to be born. There is no simple reaction that releases the entropy that is pent up, that could be created from that carbon dioxide. But there are complex systems, networks of reactions that could do it. So what you need is a certain complex structure of enzymes and catalysts in just the right configuration to let the fuel be released and combusted in that entropic reaction. And he says that the first complex structures that allowed that to happen were the precursors to life. This is what is called the metabolism first view of the origin of life, as opposed to the replication first point of view. Nobody knows which is true, but we're working on it. One of the benefits to Russell's point of view is that he said, if I'm right, he was trained as a geologist, he says, if I'm right, there are probably on the Earth today the same kinds of environments that I imagine this kind of process happening in. They would be underwater on the ocean floor, deep, warm, alkaline hydrothermal vents. So these had never been found. We had like very, very hot hydrothermal vents. We said they can't be too hot or that would destroy the chemistry. They had to be pretty warm. Let's go look for them. No one listened to him. They didn't go look for them, but they found them by accident anyway. This is the Lost City Formation. It's on the bottom of the Atlantic Ocean. It is a warm, alkaline hydrothermal vent of exactly the kind that Russell predicted would be the kind of place where life could have started. Doesn't mean he's right about the origin of life, but it's how science works. You make predictions, and you go from there. What it means is that the fact that entropy is increasing doesn't mean that it's weird that life formed. Once again, it might be that the reason why life formed is because entropy tends to increase. And once you get there, of course, our current existence as complex structures, as living beings that are moving and carrying on our day-to-day tasks of life, owes itself to the fact that entropy is still increasing, okay? We used to think, some people used to think 150 years ago, that life was kind of like a fluid. There was some life force that entered a body and left it and so forth. Just like we thought heat was a fluid, went from one body to another. We later learned that heat is not a fluid. Heat is a way of talking about the thermal energy inside a collection of atoms and molecules. Likewise, we now know that life is a process, not a substance. It's like burning a candle. Where does the energy in the candle go when you snuff it out? It doesn't go anywhere. It's still there. But the process has changed into something else. When life exists here on Earth, like you and me, what's happening is we get energy from the sun. That's the way we usually think about it, right? But the fact is, we give back to the universe exactly as much energy as we get from the sun. We radiate back into space. If you ignore global warming for a second, we radiate back just as much energy to the universe as we get from the universe, mostly from the sun. So we don't net gain energy from the sun. What we get is entropy in a particularly action-packed, low entropy form. We get visible light from the sun. So for every 1 photon of light we get from the sun, we radiate back 20 photons to the universe. But we radiate back infrared photons with, on average, 1/20th of the energy each, compared to the visible light photons we got. Which means that we've increased the entropy of those photons by a factor of 20. So we get a photon, we use it to photosynthesize, to chew our cud, to read books, to give lectures, and then we give back that energy to the universe in a much higher entropy form. We have used the useful energy in its low entropy form to maintain our existence, to maintain us moving around and thinking and talking. Everything we do increases the entropy of the universe. And vice versa, we help the universe increase its entropy. So life, even though it is very organized, doesn't work against entropy. It works hand in hand with the fact that entropy is increasing. Okay, so some of you, I'm dividing you into groups. Some of you may even be willing to take this part of the journey with me. To say, okay, I believe you, the past is different from the future because of entropy. I believe you that complex structures exist because of entropy increasing. I believe you that even life could form, but what about thinking? What about consciousness? This is the biggest stumbling block right now for many people to believing that you and I are collections of particles interacting by the equation on the t-shirt, by the core theory equation. And of course, if you didn't know anything about the universe, if you didn't know anything about the laws of physics, but knew the current configuration of stuff in the universe, and someone said, what is the thing in the universe that would be hardest to understand? You would probably say consciousness, because the human brain is the most complicated thing that we know about. So of course we don't understand consciousness. We don't understand where it came from, how to define it, all the different aspects that go into it. So I'm not going to tell you what consciousness is or how it works. What I want to try to tell you is there's no reason to think that anything that we know about consciousness is reason to doubt the fact that we are particles obeying the core theory. Okay? The fact that consciousness did arise is one of those things which, again, in retrospect, makes perfect sense, given what we know about the universe. So think about this little guy. What I want to do is give you a couple of moments in the history of consciousness. This is C. elegans. It's a favorite biological model organism, a nematode, a roundworm. And why is C. elegans so awesome? Because what we would really like to understand is the human brain, okay? The problem is the human brain has 85 billion neurons in it, all talking to each other. So there's something called the connectome, which is the list of every neuron and how it connects to every other neuron. So if you imagine 85 billion neurons, each connected to 1,000 other neurons, there's a lot of connections going on. That's hard to figure out, but this is one of these billion-dollar projects that are going on, mapping the human connectome. It's going to take a long time. Meanwhile, the nematode has 302 neurons. So we can map not only every neuron, but the connection between every neuron. We have mapped the entire nematode connectome. You can download it on your phone. That's where this image came from. There's an open source app called, guess what, OpenWorm. And you can add your thoughts to about how the nematode connectome helps it go through the day. We're not to the point yet where we can read the mind of this little worm, because there's one thing to know the roadmap, there's another thing to know like what traffic is flowing and stuff like that. But nevertheless, there is a paper, that I don't know whether how respectable it is or whether it's caught on or not, but it's provocative. It says the following thing. They can isolate a single neuron out of these 302, one neuron called DDA. This neuron's job seems to be to tell the difference between forces acting on the nematode from the outside world and forces from inside itself, endogenous and exogenous forces, okay? If the nematode is being pushed by something, is that because its muscle is twitching, or is that because it's running into a rock, right? Clearly, this would be an interesting and useful thing for the nematode's brain, as it were, to be able to understand and deal with. But also, if you use your imagination, you can see how this kind of thing might be classified as the first glimmers of self-awareness. The first moment when a living being, not chronologically first, because these nematodes are around now, we don't know where here in the history of evolution, but the kind of primitive differentiation in the thinking of a biological system of here's me, here's the outside world. Self-awareness, representing one's self as an image in one's mind. You can see how this would be extremely evolutionarily helpful to be able to do. And if you give it just that little tiny bit, it's not that hard to imagine it arriving. And once it arrives, of course, evolution gets to work on it and improves it more and more. You want to have more than just, is this me or this is the outside world? You want to know, like, how am I feeling? Am I hungry? All these various different things. And these are the steps on the way to consciousness. Here's another plausible step. This is Tiktatik rosier. This is a fossil that was recently discovered. This is arguably one of the first fish to climb up on the land and look around and start walking, okay? So there's a guy at Northwestern named Malcolm McIver who points out the following thing. If you're a fish swimming around, you can see, but you can't see that far. Fish have eyes. Eyes appear all the time over the course of evolution. But you can see tens of meters at most. That's the attenuation length of light in water. And you're swimming in meters per second if you're a fish. So if you're a fish and see something, and you have no choice, you have to react to it right away. Is it friendly? Is it going to eat me? Should I eat it, right? But then you crawl out onto land, and suddenly you can see forever. You can see for kilometers. The attenuation length of light in air is essentially infinite. So this opens up a new way of thinking. There's a new evolutionary pressure that says if you develop the ability, not just to see something and react right away, but to see something and say, how should I react to that? Let me think of the different possibilities and then choose. Then you will have an evolutionary advantage over your competitors who just think and react right away, because you can think a little bit more subtly. In other words, when you crawl up onto dry land, there's pressure to develop the capacity for imagination, the capacity to represent yourself not only as you are right now, but in hypothetical future circumstances. And he actually, again, made a testable hypothesis. He predicted that there was a certain evolutionary change in the shape of eyeballs once fish crawled up on the land for the first time. There's a paper coming out next week that says that, in fact, yes, this is what happens. Again, does this show us that consciousness is purely physical? No, it does not. But you can kind of see how the story is beginning to take shape. One thing we know for sure is that, again, there are particles inside our brains, right? This is, on the right, this is just an artist's, I don't know, maybe this is an actual neuron. It's just there to let you know there are neurons. This is actual data. This is evidence that I have a brain in my head. David Tupple, a neuroscientist at NYU, put me in a machine, an MEG, magnetoencephalogram machine, and he played noises, and he looked for small magnetic fields appearing right outside my skull. So these blue spots and red spots are tiny magnetic fields right next to my head. Why is that? Well, if you think that what a thought is, the word thought refers to things physically happening in your brain, then there's chemical signals moving down neurons. Those are charged particles. And any physics students will tell you, once a charged particle starts moving, they make a magnetic field. So this little picture on the right is a reminder that what's happening in my brain when I'm thinking is described by the core theory. It is particles coupled with fields that we know about. Maybe there's other stuff going on there too, but there's a one-to-one correspondence between thoughts and things going on in my brain. Once you accept that, you begin to wonder, do you need anything more than that? Famously, this guy on the left, René Descartes, did think you need more than that. He is known in the history of philosophy as the primary exponent of mind-body dualism. Descartes said, there's the body, but I can doubt the existence of the body, right? He says, I can doubt almost everything. What can I not doubt? That I am because I'm thinking. So if I can doubt my body but not doubt my mind, the mind must be separate from the body. It's not really very logical, actually, when you go back to it, but he put forward this, and at the time, in the 1600s, one of the things you had to do was sort of hustle for a living if you were a famous philosopher. There weren't a lot of tenured positions. So he got to know this woman in the middle, Elizabeth, Princess of Bohemia. Now, in a different world, Elizabeth would have become a world-famous philosopher or scientist. She was quite brilliant, very well educated, but she was a princess and a woman at a time when those people did not become famous philosophers or scientists. What she did was read Descartes' books, and he was hoping that she would say, that's great, here's a bunch of money. Instead, she said, I don't really agree with your books very much. She critiqued Descartes' mind-body dualism for a very simple reason. She said, if you really believe there is an immaterial mind, something that has no location in space, and you agree that we all have bodies with brains and so forth, how do the two of them talk to each other? The interaction problem. How does the immaterial mind affect the motions of the material body? When I talk or write, it's my body that is doing the moving. If you think my mind affects that in some way, they must communicate somehow. So Descartes drew this picture. This is a picture, that little teardrop-shaped thing is the pineal gland. It is the one part of your brain that is not in two different hemispheres. There's only one little gland. So Descartes said, clearly that's the radio receiver in your brain. That's where the brain hears signals from your immaterial mind, which then gets sent to your brain. Nobody believed it back in the 1600s either, in case you're skeptical right now. This is not a very popular theory, but you see the extent to which he was forced to make things up in order to make this theory work. The correct explanation for this question, for Princess Elizabeth's challenge, has never been given. No one has ever explained how the separate mind is supposed to influence our body. The modern version of it is, here's an equation of the core theory. This equation says that there's a certain collection of atoms, electrons, and protons and neutrons in my brain doing certain things. This equation is going to predict what they will do next. If you think there is an immaterial mind that is influencing me, then this equation can't be right. There must be new terms that you write down that say how the electrons and atoms get pushed around by the mind. No one has ever proposed what those new terms of this equation is. One suspects that it's not going to happen anytime soon. So, to end, I have good news and bad news. Let me start with the bad news. It's always good to end on the good news, I think. There's more bad news than good news, but the good news is really good, so that's okay. So here the bad news is, we're all going to die. And I mean that, like, not in the fun way of dying, like zombie apocalypse, or robot uprising, or ill-considered 3 a.m. tweet that starts a nuclear war. I mean, just the prosaic fact that someday our lives will end. We have a lifespan. If everything I've said is true, it seems like, in some sense, abstract physics and philosophy and so forth, but there's very down-to-earth consequences. If you're made of atoms, and life is a process, not a substance, and there is no immaterial mind, then when your body dies, you die. There is no place, according to the tenets of the core theory, for the information that constitutes your memories and your feelings and so forth to go after you die. They're there in your brain, which lies under the ground or wherever. So death is the end, according to this picture, and I don't shy away from saying that. I think it's a very important conclusion to think about. I think that as a culture, we don't do nearly as good a job as we could, taking seriously the fact that someday we are all going to die. Just to make it sound more sciencey, here's a plot. This is a plot that biologists have developed. There's a wonderful set of discoveries in biology on scaling laws. It turns out that if you're a kind of animal, let's take mammals as one example, the bigger you are, the longer you live, but the bigger you are, the slower your heart beats, okay? And they are exactly, there's a power law, a 3/4 power law that you can try to explain using network theory and stuff like that. But the interesting thing is the effects exactly cancel. The bigger you are, the longer you live, the slower your heart beats. So the total number of heartbeats you get is the same. Whether you are a mouse or an elephant or a blue whale, you get about 1.5 billion heartbeats. Okay? Now, we human beings, we've invented hospitals and pasteurized milk and so forth. So where we should live is, given our heart rates between 50 and 100, we should live about 35 or 40 years, and which is what we did live back in the state of nature. These days, with healthcare, we live longer than that, so we're up here, twice as long, 75 or 80 years. But guess what? Still only gives us 3 billion heartbeats to our lives. And I think I said that, there we go, 3 billion heartbeats. So that's the bad news. Because why did I pick 3 billion heartbeats? The statement that we live for 3 billion heartbeats is just an average, okay? Don't go home and use this as an excuse not to exercise because you don't want to get your heart rate up. It's not like that. Saying that we live on average for 3 billion heartbeats is just the same thing as saying we live for 75 or 80 years. But the point is that 3 billion is kind of an evocative number, right? And a heartbeat is an evocative unit of time. You've squandered several thousand heartbeats during this lecture already. To many people, the fact that you get 3 billion heartbeats and that's the end is depressing. It's sad, it's disenchanting. To me, it's kind of wonderful. It's kind of, very focusing of the mind. It's very inspiring to think that we only get a finite amount here on Earth. The idea that 3 billion, that's a big number, but it's not such a big number. If that's the finite number we get, then I think that it inspires us to take every one of those heartbeats a little bit more seriously than we otherwise would. So one final piece of bad news. Here is a blow-up version of that picture of the universe right now. This is the Hubble Ultra Deep Field. So if you take a camera, go out in your backyard, point it at a blank spot in the night sky, push the shutter open and keep it open, then as long as your camera is attached to the Hubble Space Telescope, this is the picture you will take. Even pointing at a blank spot in the sky, you will see that it's actually alive with galaxies. I said 2 trillion galaxies in the observable universe, about 100 billion stars in every galaxy. So every one of these spots here, even the tiniest spot, obviously the big ones, but even those little tiny ones are galaxies with hundreds of billions of stars in them. So who knows how many of them have lecture halls where they're showing pictures of us. I wonder if there's any life out there. We don't know. So the bad news is that the universe is way bigger than we are. We're not important as far as the universe is concerned, okay? We're not why. It makes no sense to me to look at this picture. There's 100 billion stars in our galaxy, 2 trillion stars in the observable universe. Look at this picture and say, I know why it's like that, so that I could be. Okay? It's probably not the right answer. But the good news is that despite our smallness in both space and time, we did take that picture. Right? We used the capacities for self-awareness that we developed in our brains to learn about the world, to develop laws of nature and understanding of the world, and make technology, and then chose to spend money sending a telescope into outer space just because we were curious. Just because we wanted to know what was out there. This is not going to help us build a better iPhone or cure cancer or anything like that. We just want to see what's out there. It's kind of a remarkable thing that we chose to do with our short allotment of heartbeats here on Earth. And I think that that's what makes us special. It's not that we're big, or it's not that we're the reason why the universe is here. It's that we're the part of the universe that has developed the capacity to think about it and to do something about it. And if we choose to keep doing that in the right way, we will make all of our heartbeats very worthwhile. Thank you very much. I'm happy to take a couple of questions. There are good questions. Yes?
The current theory, does that leave any room for anything remotely resembling free will?
Yes, free will. Okay, sorry, I was running out of time, so I skipped exactly one slide, and it was about free will. So thank you for asking me that question. So, in the book, I proposed the phrase poetic naturalism to describe that point of view here, which is that, as we've seen, there's only one world, the natural world, but there are many ways of talking about it. So to me, free will is just as real as tables and chairs. If you want to describe the universe in terms of the core theory, you will never use the words tables or chairs, right? You will use words like electrons and space-time and stuff like that. Likewise, if you want to describe the world in the language of the core theory or the language of neurons and biology, you will not use the words free will or choices. But if you want to describe the world in terms of human beings, which I think is a perfectly legitimate way to talk about parts of the world, you can't talk about human beings without talking about them making choices. Even the most anti-free will campaigner is constantly saying things like, you shouldn't talk about free will. Well, what does that mean? Shouldn't. I'm just going to do whatever the atoms in me are going to do if you don't believe in free will. The point is that you shouldn't mix up vocabulary. So you shouldn't start a sentence in one vocabulary and end it in another one. You shouldn't say, I can't choose what to have for dinner tonight because my atoms are just obeying the rules of the core theory, right? You can talk the language of people or you can talk the language of atoms, but you shouldn't mix them up at the same time. And when you talk about people, the way I put it is this. Say you go on a date. Say you have a blind date, okay? And your date says, tell me about yourself. You could say, well, you could start by listing all of your atoms. I have this atom of sulfur in this position with this velocity. Okay. You could do that. No one ever does that. No one who's not at Caltech ever does that. But there's another thing that you could do, which is to tell stories about who you are, which is not only just as correct, it's enormously more informative, right? That's an emergent description of the world. Free will is absolutely a part of the best emergent description we have of human beings. Therefore, it's real.
Is that what you're saying? We have multiple realities?
Yeah. It's multiple ways of talking about reality, is the way that I would actually say it. Who's next? A little bit younger? Yes? No? All right.
I'll direct you to Entropy. We had Entropy and then Laplacian.
Yeah.
I know that's not an actual interpretation, but where would you say we were on?
Yeah, I don't know.
Okay.
I don't know, sorry. I mean, it's a classic question. I know it's a good question to ask. Where did I write it? Yeah. We know that we're pretty darn complex, so I think you could make an argument that we're up here. I don't know whether we're here or whether we're there. I think we're here. I would like to think we're there, but I just drew this picture in PowerPoint, so I don't know. It's not dated, right? So that's future research. That's what I'm inspiring you guys to do. So, yeah. Other questions? Yes.
So, we've all been taught that the universe is expanding as a result of the initial event. Into what is it expanding?
Into what is the universe expanding? It's not expanding into anything, as far as we know. The universe is just getting bigger. So it's very much like saying, imagine you have the number line again, right? The numbers from minus infinity to infinity. Multiply every integer by 2. So that minus 1 goes to minus 2, 1 goes to 2, etc. You have expanded the number line. But it didn't go anywhere. It's still a number line. It's still exactly the same place it was before. That's what the universe is like. New space is coming into existence, but there's no thing outside into which the universe is expanding. It is hard to visualize this, given our training as people who live in the world, but the equations of general relativity make it all pretty transparent. I wrote another book about that, which you're welcome to find.
Regarding the multiverse theory, would that take place on the same time frame that our universe is going through with Entropy?
Good. So yeah, I didn't talk about the multiverse specifically in this talk, but it's definitely part of one of the plausible explanations for why the Big Bang had such a low entropy, right? Where's that? Yeah. there. One of the reasons why our universe might have begun in a low entropy Big Bang is because it came out of a bigger universe, and it's easier to make small low entropy universes than big high entropy ones, maybe, plausibly. The time, if that's true, which we don't know, but if that's true, the time scale over which these universes are likely to be created is much longer than the current age of our universe, than the current time between the Big Bang and today. So if you just look at the picture, right, of these time scales, so it's 10 to the 10 years. Cosmologists don't care about more than one significant figure. So 10 to the 10 years between the Big Bang and today, 10 to the 100 years before the last black hole evaporates. How long will it be before you make a new universe? Maybe something like 10 to the 20 years. So our universe is really, really, really young compared to any of these cosmological time scales. So it will be happening, I'm not quite sure what your question was, the whole thing is happening together in one time coordinate, but the different rates and times at which things happen are widely disparate. Yes?
I'd really like to talk just off the bat, so thanks for coming here. I was wondering with respect to evolution's role in understanding consciousness, do you have any insight into, I guess, what compels that same, I guess the first fish that you talked about? I guess what compels evolution, if you could say it like that, to say keep one creature staying as a shark? Well, I guess I'm thinking about it in the same environment. What would compel one
Right.
creature to be, develop wings while the other becomes a great ape in the same environment?
Yeah, I mean, in some sense, it's a good question. In some sense, evolution is very, very, very analogous to a search strategy on a computer, right? There's the space you're searching through is the space of all possible genomes, space of all possible genetic information. And the thing you're searching for is, what is the highest fitness organism I can make, given this environment that I'm in right now? And the way that evolution does it is, as well known, it's mindless, right? You reproduce and you randomly vary from genome to genome. There's mutations that are essentially random. And almost the vast majority of the time in mature organisms, mutations make you worse off, okay? Mutations, we tend to be in pretty good adaptation to our environment. So a random mutation makes us sick and we die. Sometimes you get a small mutation that makes us better off, but it's rare. So if you have a population of animals or plants or whatever that live in different parts of the world, the chances of the same mutation happening in exactly the same way is very, very small. So you could have either one little group of things learns to develop wings and they all start flying, or even within one population, some of them develop wings and they like wings so much they think that wings are really sexy and they stop mating with the people who didn't have wings and they just go off their own way to make a whole new species. So evolution is sort of, you can think of it as a million little points populating some landscape, what's called the fitness landscape, where the highest points of the landscape are the fittest, and they sort of climb up to the highest peak, except sometimes evolution pushes them off and they find another peak somewhere else. So there's wonderful mathematics associated with this, and as far as we don't know all the details of evolution, but it's actually a very efficient way of finding very highly adapted organisms to the environments. Yes?
When I'm looking at your things governed by the core theory versus macroscopic world, and having just been lecturing on quantum mechanics and chemistry, we give up on quantum understanding pretty darn low. When we're actually doing quantum chemistry, we very, very quickly lose the ability to take the Schrödinger equation and actually mean much by it.
Yes.
We end up with things that are mathematically useful, but with no actual comprehension of what they mean. So I think we lose the microscopic world pretty darn low down in terms of our comprehension of what's going on.
Well, so on the one hand, in some sense, that's certainly true. On the other hand, of course, we're very prejudiced by being large classical microscopic objects. To us, the regime where quantum mechanics becomes very important is low down. But there's many, many orders of magnitude lower down you could go until you reach string theory or quantum gravity. So from our perspective, that's like saying, galaxies are big. Yeah, to us, a galaxy is big. To the universe, galaxies aren't that big. I would say that's a good example where it's all relative. You might make a good anthropic argument as to why life appears in relatively classical regimes of the universe. But I don't know exactly how to make that argument, but maybe you could. Okay, we'll take 2 more questions. Yes?
Taking free will into consideration, do you think you could figure out what a person knew a year ago if you were to apply the core theory to them?
In practice, of course, no. So the question is, could we apply the core theory and figure out what we're doing in the past? Definitely not. Laplace's demon is not supposed to be realistic or even a goal to shoot for, okay? You could even do little mathematical exercises to show that the only way to calculate what will happen in a system by being Laplace's demon is to build what you think is a computer but ends up being an exact simulation of the system itself, letting it go for the same amount of time. So if you really want all of that detail, there's no sort of computational efficiency involved that lets you get there in the real world. If we live inside a simulation, that there is a much more powerful civilization that made us and their laptop, then maybe they could do that. But inside us, there's no way of using the core theory to learn about what people do. The numbers become very, very ridiculous very, very quickly. Let's just put it that way. One more question. Yes?
So when you were talking about the patterns in the whole world, all instead of patterns such as the billiard balls, for example, that only goes back so far, right? I mean, you can't trace back to before the Big Bang, right? So how does that fit into everything called patterns? Is there some way which will agree, falling the billiard balls back, then they're all connected together, then it no longer applies because you can't go back further?
Yeah, absolutely. So the core theory very, very, very explicitly applies to everyday life, conditions in this room right now. The Big Bang doesn't count. Black holes don't count, dark matter doesn't count, there's a bunch of things that don't count. So we certainly don't claim to know what happened at the Big Bang. I think, most of my colleagues agree, that someday there will be equations that tell us what happened at the Big Bang. It may or may not be the case that the Big Bang was the beginning of the universe. That's a very open question. There might have been something before the Big Bang, where we're talking about the multiverse as an example of a theory where our Big Bang is the beginning of our local region of the universe, not the whole thing. But it's also very possible that the Big Bang really was the beginning of everything. We have candidate equations on either side. We have no way of judging which, if any, of them are true right now. And not knowing what is happening in the universe is a perfect place to end. Thank you very much.